Okay, so our talk today is about managing infrastructure in the stream environment. Our two speakers are Caroline Ubing, who is a hydraulic engineer at the Bureau of Reclamation, Sedimentation and River Hydraulics Group. Much of her work focuses on 2D numerical analyses of river restoration and riverine infrastructure projects. Dr. Joel Sholtes is a engineer, hydraulic engineer and fluvial geomorphologist. He is currently an instructor of civil engineering at Colorado Mesa University and is in partnership with the University of Colorado Boulder. Joel used to be with the Bureau of Reclamation, Sedimentation and River Hydraulics Group. So with that, I will turn it over, and I think Caroline is going to take it away from here.
Great, thanks Toby. Thank you everyone for joining us today. We are here today to talk to you about managing infrastructure in the stream environment with the idea of how can we better manage our infrastructure to be more resilient to flood and disasters, and also how it can better interact with the stream environment. So the purpose of our presentation is to introduce these two documents that have been published. The one on the left is the larger document. It's about 65 pages, and it goes into great detail on each different infrastructure type, on what are challenges associated with each type, and then what are some potential solutions. So our goal today is to give you an overview of these guidance documents and to give you an idea of what resources are available to you as a communication tool, but also as a designer. So this report was also then published as a companion paper in the JARA Journal, which is shown on the right. We were fortunate enough to work with a really great team on these publications. And so you can see here we have a list of 6 different authors ranging from 4 different entities. Furthermore, we have an extensive peer review list that come from several different entities ranging from state governments, consulting firms, federal governments, and university. So a lot of experience and expertise was brought into this document. And this all stems from our, the U.S. Secretary of the Interior on the Advisory Committee on Water Information, who is the publisher of the document, and from the Subcommittee on Sedimentation. So we had an individual work group on environment and the infrastructure. So the purpose of these papers is to introduce managers and planners to best practices associated with building, maintaining, and repairing infrastructure. So as new infrastructure is built and old infrastructure is replaced or repaired, we have this excellent opportunity to increase both the infrastructure resiliency and also to improve upon its impact or decrease the impact to the riparian ecosystems. And so we tend to educate managers going through 5 different steps. So first we want to introduce them to large-scale fundamental principles of river processes and ecosystem functioning. We then want to provide them with a decision tool or a framework on how to replace, repair, and build new infrastructure in a way that takes the stream environment into consideration. We then apply that tool work to examine challenges and solutions associated with 11 different infrastructure types. Now these 11 types are discussed more thoroughly in the paper, but we will only touch upon them for the purpose of this presentation. We want to discuss how we can best manage riverine infrastructure under uncertainty, both hydrologic uncertainty and condition uncertainty, and then discuss disaster recovery and response. So we spend a lot and invest a lot in repairing and building new infrastructure. So we want to ensure that these expenditures are made wisely and in a way that is both best for the infrastructure and for our ecological system. So let's get started. We'll first discuss the fundamentals of river processes and ecosystems. As many of you are very familiar with this, we will go through this rather quickly. So first I want to introduce to managers the idea of a stream corridor. The stream is more than just the wetted channel. It is made up of several components, including the channel, the floodplain, riparian zone, and the uplands. And we want to introduce managers to the concept that these systems are all interact on both a temporal scale and a spatial scale, and they interact both longitudinally along the river moving downstream and laterally across the river width. To do this, we introduce the concept of dynamic equilibrium and channel response. So we really want to stress to our management community that streams are not static features. The banks will move and it will degrade and upgrade. And so we want to stress that these active systems are capable of transporting, storing, and remobilizing sediment, wood, and nutrients. So for example, if vegetation is stripped from riverbanks, it is likely that that river is going to widen. The converse is true. It'll deepen where vegetation is very dense. We also expect to see meander bends migrating downstream and across the valley bottom. So while we recognize that these streams over long periods of time will be relatively stationary in terms that they have average widths and average meander bend lengths, on the short time scale, which is typical of most infrastructure projects, we should expect to see some movement. So we really want to stress this concept by introducing managers to lane balance, which I'm sure you are all very familiar with, focusing on the fact that stream form in alluvial channels results from the interaction of channel shaping factors, such as flow and channel slope, with resisting factors, such as bed material size and incoming sediment load. So if we see a large change in any of those four factors, we're likely to see a response from the channel in either aggradation or degradation. We want to give managers a little bit more of idea of how these streams will change using the channel evolution model. And so this model describes how streams will attempt to reach an equilibrium as a response to a disturbance. We also want managers to be aware of what those disturbances could be. So this includes changes to magnitude and frequency of floods due to urbanization. It can also include physical changes to the channel, such as channelization and confinement by floodplain encroachment. We also want the scientific community and managers to be aware that there is now an updated version of this channel evolution model with a stage 0, depicting an anastomosing wet woodland or grassed wetland that was introduced by Brian Kluwer and Colin Thorne and published in 2014. So with that, we then introduce the idea of a channel planform to managers. We want them to understand how different channel planforms are likely to move and behave in different ways. So if they have a good understanding of the fact that a braided anastomosing system is going to be very dynamic and it's going to move a lot, they might know that this is not a great place to put a bridge. You're more likely to have success and to have a stable channel in a straight singular channel.
Great. And, you know, a lot of the paradigm that we've been taught over the years is that channels are typically single threaded and that they have this orderly transition from headwaters to main stem to maybe coastal regions. And this has informed over the last decades, maybe in the 20th century, our concept of what a reference condition is for a stream. However, in the last decade or so, there's been a lot more discussion. Caroline mentions the Kluwer and Thorne paper, where we're trying to update our concept of channel evolution to account for the fact that channels might have been much different, and we have a lot of evidence that they were different in many situations than we think of them today, and then as we see them today. Pre-settlement, pre-European settlement, rivers were much more messy. They had more large wood in them, more riparian vegetation. Beaver dominated North America in almost all river courses and had a really intense presence in terms of creating situations for wetlands or multi-threaded wetland type of conditions. Next slide, please. Thank you. And so the idea of a single thread reference condition is probably not accurate in a lot of situations, certainly not every situation. And so by adding the fact that pre-settlement we had much more wood, beaver, and multi-threaded situations, this was potentially a reference condition in a lot of our systems. Another part, a really important part of understanding river processes is understanding what the natural flow regime is for a particular river. Natural flow regimes, or any flow regime that supports a functioning river ecosystem, has many components, including the magnitude, frequency, and duration of floods, of high discharges and low discharges, the timing of those flood peaks. In the Rocky Mountains, we have a very strong snowmelt signal, and that's very common in big mountain systems. In other areas, floods might be scattered throughout the year as a result of precipitation, as well as the rate of change of floods, how quickly they rise and fall. All of those can be influenced by flow regulation, by urbanization, changes in hydrology to the system, wildfire, for example. Some of these might be long-term changes or transient changes. And so understanding the context of the flow regime and how that influences the physical environment and biological environment is important. On the right side of the screen, there's an example of altered hydrographs. So discharge on the y-axis and days of or months of the year on the x-axis. And it shows that for the Green River, we have a fully regulated system, which would be the red line compared to the blue line, pre-dam and post-dam. On the Yampa, it's largely unregulated. And then downstream of the confluence of the Yampa and Upper Green, we have a kind of a mixed flow regime that's impacted by the regulation on the Upper Green River, but supplemented by flows from the Yampa. Another part of understanding river processes is understanding the hazards that they pose to infrastructure and to development within the river corridor. This is just an example of a stream crossing that, while it's an open culvert, which is great, we might have a natural bottom there. The channel decided to go around this stream crossing and erode the road and take it out. So perhaps this was sited in an area where flow was constricted in an unnatural way and resulted in the ability for the river to move around this ridge structure as a result of a flood. So characterizing hazards as part of understanding the processes in rivers is going to be important to understand how to manage them and construct them. So we have existing tools which typically focus on inundation hazards. So this might be the 100-year 1% annual exceedance flood map, floodplain map that is part of the National Flood Insurance Program and FEMA. That is one example of flood hazards. Another is fluvial geomorphic hazards. And these could be delineated by understanding geomorphic processes. They typically aren't mapped as a rule of thumb. However, certain states have taken on the initiative to create methods for mapping what we might call the fluvial hazard zone. And this would be a zone where the river could move as a response to the flood. And we have an example of this on the St. Vrain River in Colorado, where the river took a new course across the valley and a avulsion occurred. And the river moved outside of the previously mapped inundation floodplain from FEMA. And so this was a hazard that hadn't been mapped or considered based on existing floodplain maps. And so considering the fluvial hazard zone is important, as well as the inundation hazard zone, to characterize fully the hazards within a river corridor. And this is what that might look like, where we have in green the active river corridor delineated as the geomorphic floodplain that the river might occupy during a flood or gradually over time as meanders move across the floodplain. And then attached to that or appended to that would be an erosion hazard buffer, where erosion could occur into upland areas such as terraces or hill slopes that might be high above an inundation floodplain. Nevertheless, they might be susceptible to fluvial hazards in response to a flood.
So now that we've discussed the hazards to the infrastructure with our readers, we then want to introduce concepts associated with riverine ecosystems. How do they function? What makes them healthy? What is a degraded system? So we do this by discussing habitat heterogeneity and how it's coupled with biodiversity. So we want to stress to our readers that having all of these little pockets of habitat that are all interconnected and slightly different can add to the biodiversity and encourage different species and a variety of different organisms to be living in the area, which contributes to the health of that system. So we also want to stress physical complexity, that idea that Ellen Wool has introduced of messy streams. We've had in our head for such a long time as a society that a healthy river is a clean, single channel without debris in the channel. Well, we're finding, and current research is showing, that this isn't necessarily the case. We want to see wood in the channel. We want to see big boulders. We want to see vegetation hanging into the channel. And so introducing and stressing those concepts of lateral and longitudinal connectivity and continuity of all water, sediment, and nutrients. All of that nutrients that's in the floodplain then comes into the river to feed the macroinvertebrates, to then feed the fish. Also, the continuity of sediment and nutrients downstream. The sediment is held in the reservoir. It's not going to move downstream. We're going to see scour downstream of that reservoir, which will then move all of those particles that are beneficial to fish species. And so restoration is so important these days, and a lot more focus has been put on restoration these days. We want to ensure that our projects are actually successful and are actually accomplishing those ecological goals. So previously, a lot of river restoration projects have looked a little bit something like this. You have this beautiful, single, sinuous channel with almost a perfect sine wave. Well, we're arguing now that that's no longer beneficial, or may not be beneficial to the ecological goals associated with the project. So these restoration practices focus on stability and the idea of a single stable channel, whereas what might be more beneficial to the ecological system might be something that looks like this. And you can see it's messy. There's not a clearly defined channel. There's a lot of wood in the channel. Vegetation is growing everywhere. But this offers a lot of different pockets for different species to reside in. So what we're proposing is to go from our status quo that looks something like this into something that's a little bit more resilient and beneficial to both the infrastructure and our stream systems. So let's look at this figure in a little bit more detail. Starting on the left, we have a channelized reach with a road right next to it. Because we don't want to compromise that road, it's heavily rip-wrapped, and we have the suspended pipeline going across the river. Now, if anything were to move on this river, I'm willing to bet that that structural integrity of that pipeline would be compromised. Same goes for the levee. It's right next to the river, and if there were to be any bank erosion on that area, the levee could be compromised. Moving along the photo, we have blocked fish passage at our diversion. We have cattle that are grazing directly in the river, which is likely exacerbating any bank erosion problems that we will see. Our bridge embankments constrict the river. So again, if that river were to move at all, we could see a similar situation to the previous photo, where the river then completely abandons the culvert or the span in the bridge. We're proposing a little bit prettier of a picture, in my opinion. So looking at this river channel, we have this riparian vegetation along the entire length of the river. This is beneficial to the river because it can filtrate any pollutants from runoff, either agricultural or urban runoff. It is also beneficial to the infrastructure because those roots reinforce the strength of those banks, hopefully creating a slightly more stable channel. But we're not relying on a stable channel in this photo. We can see that our road has been moved away from the channel. Our levees have been moved back and possibly removed where appropriate. We also see that we have a wetland that has been restored, so if the river were to move, it's okay. We see that our riprap has been removed using bioengineered bank stabilization instead, which offers more habitat opportunity. And then looking at our bridge, We have a much wider span, allowing the river to move underneath the bridge, and then we have some overflow culverts in case we see an uncharacteristically high storm. So this is the more resilient and stream compatible infrastructure that we want to encourage managers to consider when replacing or repairing their old infrastructure. So let's look at this decision tool in a little bit more detail. So we have 4 steps to our decision tool that we're encouraging managers to use when looking at infrastructure projects. I will now take you through each of those steps in more detail. So step 1, we want to identify project goals and scope as we would in any project. So it's very important at this point in time that we consider the social, economic, and ecological values associated with each of these, with each community. So for example, a bridge project in Western Colorado will have a very different focus than the same bridge project that could be located in a rural community in Indiana. We want to encourage managers to have stakeholder engagement very early in the project. This will allow for a more successful project and will also allow you to consider more components. Watershed master planning is also highly encouraged, and that's something that isn't done widespread across the United States yet. We want to look at the basin as a whole. Where are there opportunities for infrastructure project or restoration efforts, and where are there restraints? So if we look at a larger system when we're building that bridge, we might see that this mile stretch of river is very dynamic, it's multi-threaded, and will not likely be a good location for a bridge project. However, maybe a mile or 2 downstream, we see an area where the river converges and is a single threaded straight channel. This might be a better opportunity for that bridge. So these are the management questions that we are encouraging managers to consider. For one, how does this infrastructure affect river processes and ecosystems? 2, does the cost of more resilient and ecologically sound infrastructure actually reduce maintenance costs? So for this pipeline example right here, I can bet that it's going to be very expensive to do the repairs. Had the pipeline been built in a better location, they wouldn't have had to spend all of that money. And then 3, how can we better build, repair, and decommission our infrastructure that's more compatible with that river environment? So that leads us to the second step of our flow chart, is evaluating hazards and values. So Joel took you through many different tools that are available to designers on how to better analyze our river system to identify those hazards associated with the river system. And so unfortunately, there isn't a cookie cutter answer of you have to do this, this, and this analysis in order to have a successful project. It is very project dependent, but some options are flood inundation mapping, geomorphic hazard mapping, and mapping out that channel migration zone. We also recommend having the right team involved for each infrastructure project. Make sure there's a fluvial geomorphologist on board should the project need one. And then in this situation, we want to stress avoiding those stream impacts is going to have the most resilient project. However, we recognize that that is not always a feasible alternative. So your third step is formulating those alternatives of the projects that are interacting with that stream environment. So again, where possible, we want to design a solution that avoids all interaction. Will limit the exposure of the riverine hazard and avoid impacts to the environment. However, if these impacts cannot be avoided, we want to first minimize those impacts. So for example, reduce the project's footprint in the channel migration zone, lengthen the bridge span, etc. We also recognize that very different considerations are needed for existing versus replacing infrastructure. So in the opportunity that aged infrastructure is damaged, we can replace it or relocate it. So one option would be if a flood comes through and washes out that old barn, maybe it's not worth rebuilding that barn, or we can rebuild that barn in a different location that is outside of the hazard zone. Another example would be replacing a diversion dam with an infiltration gallery. This way, we aren't seeing a vertical discontinuity or break in the river system, and we're removing any obsolete dams. New infrastructure has its own set of challenges. We want to minimize the impact, of course, but in the case that we can't, there may be an opportunity to mitigate that impact with off-site rehabilitation. So for example, should we need to build that levee right on the riverbank, maybe there's an opportunity downstream of that location to buy back some land and create a nice floodplain system that can absorb the additional floodwaters that come through downstream of the levee. And our last step is number 4, evaluating those alternatives, deciding and implementing the project. So at this point in time, we're evaluating all alternatives based on the purpose, goal, and values that was designed and defined at the beginning of the project. These alternatives must also be evaluated by engineering feasibility, economic benefit, and environmental benefits. We highly recommend stakeholders be involved during this final decision. It'll help guarantee, well, it won't guarantee, but it will help with the success of the project. There are also many decision-making tools available to managers should there not be a clear winner. So now that we have our decision tool framework, I would now like to show you how we can apply it to different types of infrastructure types. So in the document that we showed you, we go through 11 different infrastructure types: floodplain encroachment, wood management, pipelines, levees and dikes, stream bank protection, stormwater infrastructure, channelized rivers, grade control structures, transportation infrastructure, dams and reservoirs, and then surface water diversions. For the purpose of time on this presentation, we will only focus on a few, but know that there's a lot of information available to you in those documents.
So to introduce you guys to some of the ways we're thinking about these riverine infrastructures, we'll start with large wood. And we're defining infrastructure very broadly here to incorporate concepts of green infrastructure, parts of the river corridor that serve as infrastructure, not only for human benefits as well as for ecological benefits. And we've acknowledged, we spent a lot of time in the 1800s and 1900s taking wood out of rivers for a lot of reasons: navigation, concern about clogging and overtopping, stream crossings, bridges, and the like. There's a lot of acknowledgement now, science-based acknowledgement, that large wood in rivers plays a really key role in creating habitat for multiple species, providing a food source, and playing a role in the fluvial geomorphic processes that create and maintain habitat in rivers. So wood is now being used to, in an engineering sense, to create and try to restore processes in rivers as part of restoration projects for habitat and geomorphic restoration. We're also starting to think about how to manage wood that already exists in the system that we didn't place there with machinery. And as we restore riparian areas and try to restore the process of wood and the geomorphic processes associated with that, we need to think about how to manage wood in a way that is not going to cause or reach some threshold of hazard in a river system that might, for example, undermine and potentially lead to bridge failure downstream during a flood event. So there are resources that we touch on in the guidance document that others have worked on to provide managers with tools to think about how to manage wood, how to perform risk assessments if we're in a sensitive area where wood plays a really critical role to maintain certain species habitat. How can we manage that wood in a way that reduces risk to certain structures and also allows for the benefits of large wood and river systems? Stream bank protection, another example of riverine infrastructure. The traditional sense of stream bank protection would be large stones, riprap, different engineering devices that would reduce bank erosion. Where it's feasible, where it makes sense, there are a lot of other options, and so we highlight these. There's a lot of great guidance documents out there on how to conduct bioengineering, use of live material that has the potential to be more dynamic, meaning flexible, and grow back and regenerative as well. So riprap you don't just set it and forget it. The rivers are always moving these rocks around. So this section in this guidance document draws managers' attention to different options for protecting stream banks where stream bank erosion is a concern, to protect infrastructure, and in a way that not only results in the engineering goals of reducing bank erosion where that's needed, but also to these have the potential to provide the ecological benefits that vegetated riparian corridors have in natural systems. Obviously, transportation infrastructure is a huge type of infrastructure that interacts with rivers, especially in systems where we have canyons and we have thousands of river crossings and river adjacent transportation corridors throughout our country. And so this section of the guidance document covers where are some of the pitfalls that we have and some of the concerns we have with roads adjacent to or crossing rivers. What are some of the challenges? And then what are some examples of ways we can mitigate those concerns? And a lot of it comes down to trying to look for opportunities to set roads back away from rivers on the edge, the margins of a valley where that's possible. Often this is the opportunity for this is after a flood event. And so we have an example of from the 2013 flood in Colorado, which informed a lot of our thinking about how to respond to floods in the state. And there's an example in the Big Thompson Canyon, a conceptual drawing. This has been constructed now by the Colorado Department of Transportation, where an outside bend, which is very vulnerable to scour and erosion, was moved back. So they had to do a big cut in the neck to bring the road onto the inside of the meander bend and away from that hazardous area. And now we have a greenway on that outer area where this is no longer part of a vital transportation corridor. Stream crossing infrastructure is very vulnerable to flood hazards and can also create impacts to stream ecosystems. Here's an example of a perched culvert on the left-hand side, and this will allow flood flows to go through it, but it's not allowing small fish and really probably any fish to pass through that culvert. So it serves as a barrier. And there's a lot of examples of this across the country. It's getting more attention now that certain species, habitat connectivity for certain species is getting more attention, especially in New England and salmonid areas where we have endangered species, as well as in other areas where we care about the fisheries, and put effort into that. So there's a lot of great documentation and guidance on how to design stream crossings in a way that maintains continuity of sediment, of flow, allows for passage, and also can result in a stream crossing that is more resilient to floods, allowing flood flows to pass through it as opposed to becoming a bottleneck to flow and sediment. So the U.S. Forest Service has a stream simulation guidance document that came out about 10 years ago. The Federal Highways Administration also has documentation and guidance documents on these kinds of crossings. So floodplain encroachment is, we're calling this stream infrastructure because it is technically infrastructure in the stream corridor, although we may not consider it infrastructure. It's residential infrastructure. It's perhaps roads, roadway embankments fill in the floodplain. So here's an example of Left Hand Creek as it flows into the city of Longmont. This development filled in the floodplain and constrained this creek pretty dramatically in the 20th century. And then for the next slide, please. So there's opportunities where we don't have dense urban development to look at where levees might have been created for some use that's no longer in existence. And this is an example on the Poudre River in Fort Collins, where the city is putting a lot of effort to restoring floodplains, removing levees that are no longer in service, and restoring the floodplain. So I have outline of where that levee existed. That was taken out and the floodplain excavated and revegetated, and now it's connected beautifully in a flood event that occurred in 2014. And so this, looking for opportunities, you can't do this everywhere. Obviously, we're not going to take whole neighborhoods out where they've been established in the floodplain, but acknowledging that floodplain encroachment does put more infrastructure at risk and also has ecological impacts, and looking for opportunities within river corridors to either remove or set levees back, or to take encroachment out of the way and restore floodplains. This is ecologically important. So we talked about connectivity, lateral connectivity, and this allows waters to be laterally connected to the floodplain. It can reduce flood peaks downstream, and also provides that hydrologic and ecological connection with the river and its floodplain. So for the sake of time, Caroline, I think maybe we'll skip the next two and let you wrap up for the last 5 minutes that we have.
So looking at all of our infrastructure, a lot of times these designs rely on estimates that are subject to a lot of uncertainty. We looked at the stream flow. We want to predict what that 100-year event, that 10-year event looks like so we can design accordingly. Unfortunately, there is a lot of uncertainty associated with these data. So there's many reasons. First of all, we have very short data records. A lot of times we're lucky enough to have 20, 50 years of record, whereas really we would like to see a lot more. There's a lot of land use changes that are going on that are associated with those data records. So if we see a huge spike in our stream flow, we don't know what could be happening. Maybe there's some climatic variability. Maybe there's a land use change. We also have a lot of hydrologic variability. So the traditional route of this is to just apply a large safety factor to our project and then hope that it works. This is particularly evident in riprap designs. However, this is not always the most ecologically compatible result and may not serve the project in our best interest. So we want to offer some other tools on how to manage under uncertainty. So for one, incorporating tolerances for change into our design. So instead of applying that factor of safety to the design, maybe we apply that factor of safety to the hydrologic flow. Maybe when building that bridge, we design those overflow culverts so that the design can work with a larger variety of different flow events. We also want to encourage a robust alternatives analysis. And then there are a lot of tools available to us now. There's a lot of scientists out there studying climate variabilities, studying land use trends. So using some of those models may be appropriate depending on your project to better constrain that discharge and the design parameters. And finally, we want to encourage adaptive management. This can actually be a good opportunity to save that project some money. So maybe we can start out with a low-level design. So for a stream bank protection, for example, maybe we start out with just a few plantings and see how the system responds. If it seems sufficient, then maybe we don't need to do anything else. But if we see some low-level erosion, then maybe we do need to come in with a little bit more of an aggressive approach. And lastly, we want to look at the flood disaster response and recovery. So we want to stress to managers that large floods or any damage to infrastructure is actually a great opportunity to redesign our infrastructure in a way that is more resilient and more compatible with the stream environment. So we understand that after a flood, it can be very difficult to get funding. And permitting and funding agencies are not always very flexible in terms of the post-disaster recovery. So for example, FEMA's Recovery Assistance Program will only allow reconstruction to what previously existed. Well, what happens if the river completely abandons its channel? Then that would no longer be useful. We also don't want to be replacing poor designs or poorly designed infrastructure with a poorly designed bridge. So we want to look at that previous design and to see if we can make it more compatible. So while we know that there's a lot of limitations associated with this, we want to encourage you that efforts are being made to change that policy and to rework those policies in a way that makes more sense. But meanwhile, we can do some planning up front in order to aid that disaster recovery. So if we do some watershed planning, we can then identify where there is stream infrastructure that is not compatible with the stream environment, and recognize some opportunities where we could maybe build those designs better. So we can have those designs in the back of our pocket, so when or if an emergency should occur or a disaster should come through, we're ready to build a better infrastructure. And so we want to stress to our readers that there is a lack of literature and regulations on quote unquote building back better, and this provides an excellent opportunity for future research and future actions. So that is our call to action at the end of our presentation, something to think about as we're discussing infrastructure with managers and as we're working on our designs. So with that being said, all of you know we invest a lot to repair and build our new infrastructure. We want to make sure that these expenditures are made wisely to protect our infrastructure and the river environment. So to do this, we have prepared 2 guidance documents geared towards managers and planners. We want to teach them how to better build, maintain, and repair infrastructure that is resilient to riverine hazards. So this is beneficial to the communities because less expenditures are necessary for maintenance, and it is also better for the riverine ecosystem and environment, which then benefits the community. The health benefits associated with green space has been very well documented and is quite amazing results. So this will benefit the community from that aspect as well. So in order to better communicate these concepts to managers and planners, we introduced fundamentals of river processes and ecosystems. We developed and introduced a decision tool made to replace and repair and build new infrastructure from the stream perspective. And then we introduce our readers to challenges and solutions associated with 11 different infrastructure types. We want to manage our riverine infrastructure under uncertainty, and we provide some tools on how to better do that. And finally, we want to consider our disaster recovery and response and see if there's a better way that we can respond in these situations. And with that, I would like to thank everyone for attending our webinar and for your time today. The longer version of this report is available on this website. There should be a download link there should you want to dig into this information a little bit further. And with that, I would now like to turn it back over to Toby to address any questions.
Great, thanks Caroline and Joel. That was a great presentation. Folks, if you have any questions, go ahead and post them in the either Q&A or in the chat. You can send them to me directly, so that's the host, Toby Minear. I have a couple of questions here that I'll ask to Caroline and Joel. I think, actually the first one maybe I'll ask of Caroline. There was a question about any examples of infiltration galleries. And I think that was a slide that you were presenting.
So that's something that I would refer to the document. There could be some examples in the document, but what I'm really proud of with the document is that at the end of the document, there is a long list of different resources for designers, and it's separated by different infrastructure types. And so I would be willing to bet within that list, there's some really good information that might show some better examples.
Okay, great. We do discuss in the guidance document, as Caroline mentioned, that is one of the examples we provide as a good alternative to a weir in a situation where flow withdrawal is needed. Infiltration galleries up to a certain flow rate can be potential opportunities to reduce impacts in the stream itself and also meet the flow withdrawal needs of the situation.
Okay, great, thank you. There's another question here, just wondering if there's an opportunity to get a PDF of the presentation posted.
Yeah, can we post that on your website, Toby? Or we could put it on the ACWI website. How's that sound?
Yeah, that would work. Yeah, although we're kind of redoing that right now. I think we can probably post that in the news, the announcement page, if that would work. Because we'll basically post a link to this recorded webinar there too, so we can just post the actual PDF of the presentation. If that would work.
Sounds good.
Okay. let's see, we have, okay, actually, do you want to, Caroline, do you mind going back one slide here? Just see, I was going to see if there's, oh, it doesn't look like it's on there. There's a question here in the chat asking for the Wool 2016 paper.
I'm happy to send that if someone wants to email me. It's a river flow. It's a conference proceeding paper.
Okay. Okay, so that's to Richard Evans, if you don't mind. The other option you could do, Joel, if you have it close by, is just post it up in the chat page so you can grab it. Okay, I'm not seeing any other questions.
So we don't know who else on this presentation. I assume a lot of folks already know a lot about river processes. The main audience for this document is because it's a primer, it's very high level, and it kind of serves as a clearinghouse for a lot of other reference manuals out there on designing and managing these different types of infrastructure. Our goal in doing this presentation is to familiarize you with it and have it as a reference that you can send out to the people you might interact with out there, the county, city, infrastructure folks, planning folks, DOTs and the like, as well as other agencies out there. So we did it within Reclamation and our partners with Forest Service and Army Corps and others as a way to get this out there and get it out into the regional offices and folks working on the ground on infrastructure as a resource for them.
Great, yeah, thanks. You know, that was, yeah, it's definitely a very useful document. I don't know if you saw it there, Joel, but we were posting links to it so folks could get a hold of it.
Great.
Yeah. Okay, so I think I'm not seeing any other questions here. So why don't we go ahead and end the presentation there. So thanks, Caroline and Joel, for a great presentation.
Thank you,
Thank
everyone.
you.
All right, take care, everyone. Thanks for attending. One thing I'll mention, if there's still folks on, is we have another webinar next Monday on sediment and dam removal. And that'll be with Reclamation engineers Tim Randall and Jennifer Boundary. So if folks are interested, you can find that on a similar link. I think if you just look for series and sediment and dam removal, you'll be able to find it. All right, I'll end there. Okay, take care, everyone.